Okay, we are at January 26th, 2026, and this is the Western Automation 7 a.m. Monday morning technical class. We are going to have a discussion today about precision gearing. And I just made the mistake I always make where I share the screen, but I don't include the sound just in case I want to play something. What we want to talk about today is gearboxes and gear sets, but primarily gearboxes because that's the way they're sold in our industry, as used in precision applications. This would imply, for the most part, electric servo-based applications, and drilling down a little further, electric servo-based applications using PM, high power density, low inertia motors. A servo in general is basically defined as a prime mover, be it pneumatics, hydraulics, electric, with feedback, as in an encoder, etc. So you can have an induction servo, which is an AC induction motor with an encoder feedback. The controller is now closing the loop on velocity and position. As you know, we have three basic control loops when we talk about motion control. The torque loop, which is inside the velocity loop, which is inside the position loop. You control torque and you have an encoder feedback. You can then control velocity. If you're going too slow, you increase the torque. If you're going too fast, you decrease the torque. By the way, this is very similar to how you operate in a vehicle, a car. You pushing down on the accelerator pedal is changing the fuel mixture to your engine, which changes the torque of the engine. The speedometer is the feedback, and you are the controller. That's a torque loop. When you drive a car, you're not operating a velocity loop. You're operating a torque loop to obtain a desired velocity. From velocity, we can then control position. And if we use encoder feedback again, and we go from a known spot and we count the number of pulses in one direction or another, we know the position. And using torque control to control velocity, we can then control and arrive at the position that we want. An absolute encoder differs from an incremental encoder in that you don't need a starting position. It always gives you a unique feedback for any position in the range that you want to move to, and therefore doesn't need a starting point. So basics there, but the three control loops. You will find that torque and velocity are integral to sizing gearboxes. No coincidence there. As far as precision gearboxes are concerned, let's go through some terms, and I will publish this PowerPoint at the end of the class to everybody. But we basically have to size our application based on continuous and peak loading factors. So continuous torque and peak torque. You may even have issues where you want to size it for shock load torque, which should be the ultimate strength of the gearbox before it destroys itself. The efficiency is very important. We'll go into that as well. And then you have the mass of the gearbox, which relates but doesn't always dictate the inertia of the gearbox. The inertia is very important on a gearbox because the inertia of the gearbox and the inertia of the servo motor are part of the total inertia of the load. And accelerating to speed is directly related to inertia. So that's a factor we need to understand in gearboxes. Then we have the accuracy issues such as backlash. Now, backlash is basically if you take your fingers and push them against each other, you have a space, kind of like this, right? That's backlash. And there are gearboxes that have a lot of backlash, and there are gearboxes that have zero backlash, and we'll talk about that. Backlash is if you're reading off your encoder on your motor doesn't see the backlash. That makes sense. Now, in some cases, we're going to put feedback downstream of the backlash so we can see that backlash. In a lot of precision gearing, you pay money because it's worth it to reduce that backlash. And in many cases, in today's world, because gearboxes have become less expensive based on their performance, in my opinion, we're doing a lot of very low and zero backlash applications. We'll talk about that as well with certain geometries of gearboxes. The torsional stiffness of the box, that is, let's say you have a brake on your servo motor and you clamp the brake on, and then you apply a load to the output. It is the amount of load you apply and the deflection it causes in your drivetrain. And if it causes no deflection, then you have a super stiff transmission. Most gearboxes are not quite that stiff, and you often select a gearbox for its stiffness as well as its backlash in terms of the precision you require for your application. A good example of stiffness where the customer pays a lot of money for stiffness is in the antenna application where the antenna is not in a radome. In other words, it's subject to wind. There's a lot of antenna business in this town. And when you're looking at a big dish, say a 6-meter dish, it catches a lot of wind. It's a sail. And when the wind hits that gearbox or that dish, you don't want it to deflect at all, because the antenna business today is all about hyper precision, because the signals that they're attenuating are shorter and shorter wavelengths, and therefore any inaccuracy in the pointing of the antenna on the ground, if you're trying to communicate with a satellite, it means meters and meters of error out at low Earth orbit, which is, I forget what low Earth orbit is. It's a few miles, I would imagine. So you can imagine that a small angle can result in a very large arc at distance, which is what we're talking about. There's other things that are not mentioned on this chart that you need to be aware of in terms of gearbox, especially in smooth applications. For example, torque ripple. When you apply a smooth torque from a servo motor and you apply it through geometry of gearing, it implies that the force of contact on the teeth of the gears is not consistent, which results in torque ripple. You have velocity ripple, and then you have a concept called nonlinearity of velocity, which is very important for positioning turntables. And that means that if you travel a certain distance on the servo motor, and let's say you have a 10-to-1 gearbox, just to make the math simple, do you travel exactly that 1/10 of that distance on the output of the gearbox? Number one. Number two, as the motor goes through its motion on the motor shaft, is the gearbox exactly consistent with that motion, or does it deviate a little bit? That's nonlinearity if it deviates. So you might say it's the nonlinearity of velocity, because gearboxes based on their geometry may go faster and slower and still arrive at the same point as, say, let's say you go 100 degrees on the motor and the gearbox goes exactly 10 degrees, and you'd say, oh, I've got really good linearity. But on velocity linearity, you may not, because you may have gone faster and slower relative to the motor shaft between 0 and 10 degrees on the output of the gearbox. I hope you understand that. I didn't find a good visual for that one, other than some graphs. But nonlinearity of velocity is extremely important in turntables. Nonlinearity of position is also extremely important in turntables. What does it mean? It typically means that you got to put a very expensive scale on the output of the turntable to compensate for that nonlinearity of velocity and position relative between the motor shaft and the output shaft of the gearbox. Similar to putting secondary feedback on the output to compensate for backlash. So here we have the terms of engagement on our discussion today. And we're going to move to the different types of gearboxes. I like this slide, so I'm going to show it. Typical velocity move is to accelerate, run at speed, and decelerate. And to understand what that means as far as the gearbox is concerned, we overlay a torque curve on that. And you can see that the torque is peaked out to accelerate and to decelerate, change the velocity, but reaches a relatively stable value when we're running at speed. Now, this assumes constant load, of course. So gives you kind of a visceral idea of what's happening with the gearbox. You want to accelerate fast, this is going to go way up and be shorter, of course, because the acceleration ramp will be shorter. Now you get this idea of why you need to understand peak loading on gearboxes versus continuous loading on gearboxes. And by loading, I mean the ability to handle torque. So thus we have continuous and limited duty regions when we rate gearboxes. It's so important to understand both when you size the gearbox. Here is a chart that I took off of a project that I was working on, and it tells you the relative values of the key factors in gearboxes. Here we have a position, which is ultimately what we're trying to achieve. This is the velocity that we're using. Apparently, we don't want to run at speed on this one. We just want to get up to speed as fast as we can and then decelerate. So this would be typical of an indexing move, for example. Go from point A to point B as fast as we can, increase production on the machine. And here is so we're in either acceleration or deceleration the entire time. And the torque here, in this application, continuous torque is your acceleration torque. Interesting concept. Because up here, continuous torque is more here, and there is your intermittent torque. But when you go up and come right back down again, this level of torque becomes your continuous rating. Gear reduces RPM, increases torque, and can reduce the cost of the application. Why use it if it doesn't include reduce the cost? Why wouldn't you just use a motor and direct drive everything and eliminate the gearing? Well, a lot of applications we do direct drive, and the motor that application avoids backlash and all the other things associated with gearboxes. But gearboxes are predominant in our industry in terms of motion axes. This is something we've pretty much discussed. These are the negatives of using gearboxes in a motion control application. And here, this efficiency factor is very important because it affects your sizing of the servo motor. You lose energy in the gearbox. It's the price you pay. Here are the efficiencies of the various styles of gearing. We'll look at the geometries of these this gearing in a second. I added in harmonic and planetary efficiency because I realized this chart was an old one. And I didn't realize it, but harmonic gearing efficiency and the cycloid efficiency, to me, I thought they were more like planetary efficiency, and they're not. You can see they're way off. They're kind of like worm gearing. So this is a picture of what they call an involute tooth gear. And it is the majority of the gearing that we use. However, I will show you styles of gearboxes that do not use this shape of tooth, typically cycloidal. But even harmonic gearing uses an involute tooth. Now, these are the types of involute toothed gears. And the spur is most common. The helical is a refinement on the spur. Here's a refinement on the helical. Why refine from spur to helical? Primarily noise. The efficiency is roughly the same. I find that torque ripples less with a helical gear versus a spur gear. And then we take these gearboxes and we basically turn them on a right angle. And here we are using a helical, if you will, but in a geometry that allows changing of the torque direction 90 degrees. Down here, we have a complete departure from these types of gears called the worm gear. And a further refinement of the worm gear is the double enveloping worm, which I'll show you in a second. This, by the way, this geometry, in my humble opinion, is unsuitable for precision applications. It has way too many limitations and doesn't have the significant cost advantage that it used to have. This is double enveloping versus the single enveloping that I showed you earlier. Note the shape of the worm gear. More teeth in contact, 4 to 8 teeth versus 1, because this is a tangent to a circumference, and mathematics, by definition, a tangent on a circumference of a circle is 1 point, 1 tooth. All the torque transmitted through 1 tooth. Not ideal, but inexpensive, or used to be, because this was easy to machine. This, back in the day, up until the advent of 5-axis CNC, was expensive, required special tooling, hobs. I've represented cone drive forever, and we used to hand lap these gears before we shipped them. You can imagine what that added to the cost. Now, with 5-axis CNC, the cost of double enveloping has come much closer to straight worm, but you get the advantages of extra teeth of contact. The efficiency goes up 10, 15 points. So if we go back to efficiency here, this worm here, 50 to 90%, that's representative of all worm gears. In terms of double enveloping worm, depending on the ratio, you can get as high as 90%, but typically you're in the 80s. With normal worm gearing, you're in the 60s and 70s. One caution about worm gears, and that applies both to the single enveloping or single tooth and double enveloping worm gears, is that they have a horrible starting efficiency compared to other gearboxes. These efficiencies associated with these types of gears, with the exception of worm, are pretty much consistent from start. The stiction issue and the geometry of the worm gear mean that the starting efficiency of worm gears can be as low as 25 to 30%. And you've got to size for that when you're starting out. Stiction is a term that we use in our industry for the interface between static and dynamic friction in a motion application. Static being higher than dynamic in most cases. You've known that because when you start to push a car, you have to really push hard. And then once the car gets rolling, the friction coefficient drops significantly and you don't have to push as hard. So this gearbox here versus this gearbox here, you're running 80% roughly efficiencies versus 60 to 70%, but both have starting torque issues due primarily to the stiction of this geometry. Size accordingly. Okay, now, let's take a look in detail at the planetary gearbox, because this is the primary inline gearbox that is used in our industry. And then I'm going to move to harmonic and epicycloidal as far as inline boxes are concerned. Not a lot of helical gearboxes, in other words, small pinion, large driven gear, are used in the servo industry. Typically, while we're using spur or, in some cases, helical gears for planetaries, here you have the spur and the helical, and then you have the application of the spur on a planetary and the application of a helical on a planetary. But primarily, we use this geometry for inline. This is the lower cost option for, and you can get backlash down to an arc minute on precision gearing for planetaries. But this is how a planetary operates. You have a sun gear and planet gears. So as you're driving the sun gear with your servo motor, you counter-rotate the planetary gears, and as a result, you counter-rotate around this internally toothed ring gear. Now, typically, this is the housing in most applications. So you're driving this sun gear, and now these three planet gears are rotating around the fixed housing of the gearbox. And in order to transmit torque to an output shaft, you have to put a carriage on these planet gears. This is a 4-planet gear versus a 3-planet gear. And then that becomes your output shaft. So that's how planetary gearing works. This is incorrect. It's not an epicyclic gear train. I'll have to fix that. The planet gearing has backlash, as you can see. And thus, the priciness of this box goes up and down with the precision with which the gearbox is manufactured. You can have multiple stages of planetary gears. And somewhere in here I have a, where's my, okay, so when I go back to this, the efficiency, this is per stage, okay? I note, here's the ratio you can get per stage on these gearboxes. Planetary, because it's not on here, is limited to 10 to 1. Personally, I limit planetary gearing to 8 to 1. I find that when you go beyond 8 to 1, the planet, the sun, these gears get too small in order to obtain the higher ratio. And what that means is you now have less torque transmission capability, which means you have to derate the box as you go up in ratios because the planet gears get smaller. And I find that the cost the point of diminishing returns is around 8-1. You go to 10-1, you have to derate too much. However, many people sell 10-1 planetary gearboxes. So don't just take my word for it. You have to do the numbers. In general, I've typically gone to 2 stages when I go beyond 8-1. That stage, that reduction per stage is pretty significant in terms of how you size gearboxes and how you cost gearboxes. It's a huge advantage for worm gearing, hypoid gearing, cycloidal gearing. Harmonic gearing has a similar, actually it's up to 150-1 for harmonic gearing. Planetary gearing gets expensive. So if you're doing a 100-1 application, you're either on 2 10-1 reduction ratios, so a 2-stage box, plus a lot of derating for the small planet gears in those 2 10-1 stages, or you're in a 3-stage box. Now planetary doesn't look that good when you can do a single stage with another type of gearing. Let's switch over here to a different presentation. And so when we talk about right angle versus find my ground here. Problem I have when I jump around in different presentations. So the difference between right angle and inline gearing looks like this in certain applications. It's a spacing issue. And whether the geometry required for your particular application is better suited for inline versus right angle, that's up to you. It's up to the application, but know that you can go both ways. So it's a choice, and it does have a significant effect on which type of gearbox you select. Here we have inline planetaries, and here we have a right angle, in this case helical bevel. This is a Stober presentation. Stober doesn't, I don't think Stober makes worm gears, but they do make the helical bevel, spiral bevel type. And you can see how the difference is in terms of the geometry. Now, when we talk about gearboxes matching up to motors, that's another issue we need to be aware of in terms of sizing the gearboxes. And what I find is that axial length becomes the main factor. Sorry, I'm not getting exactly to where I want, because the Stober folks basically just sent me this last night, and I didn't get a chance to get familiar with it, but I wanted to include their stuff. So let's see. We have basically it's a simple concept, and if I can't find it, I will have to just. Oh, I know what I'm doing wrong. It's in the other presentation. So, here is the typical arrangement when you buy your gearbox from one party and you buy your motor from another party, and you've got a housing and a zero backlash coupling. Excuse me. In the interface, that is going to add axial length to this assembly. It also adds cost. And, in a bunch of parts here, your flanges and your compression couplings, etc. You typically have an extra bearing in this because you got two different pieces bolted together. If the manufacturer makes the motor and a gearbox as a unit, you can then eliminate a lot of this componentry, and the shaft of this motor becomes the mounting point for the first stage of the gear. This is very advantageous in terms of axial length. It is not so advantageous when one or the other fails. Gearboxes and motors have different failure rates, and you don't want to have to replace the entire thing when one or the other fails. Unfortunately, with this, you kind of end up in that situation. You may be able to get the motor only from the manufacturer that did this, but you can't go to another manufacturer. Here, the servo flanges and shafts are relatively standardized. I'm going to say relatively because they're not as strict as the NEMA and IEC regulations for induction motors. You know, I've seen certain square flange servo motors with different size shafts, for example, different length shafts. But for the most part, you're relatively standard. You have a pretty good chance of being able to replace this motor with another motor should the motor fail versus the gearbox, and vice versa. You have a coupling in here, which makes it easy or easier than this. Here you're locked to the OEM. So there's advantages and disadvantages to both. How long should a servo gearbox last? And in my experience, you should, assuming you've rated everything correctly, the motor should last 5 years under continuous operation. Therefore, if it's intermittent operation, you're going to extend the life a little bit. The gearbox, again, within its temperature of operating range, with proper lubrication, properly maintained, I'm going to say 3 to 4 years under continuous operation. Now, not so much the motor, but the gearbox is going to vary dramatically based on how much peak torque is going to be applied to this motor in its application. So this is a very subjective discussion. But nevertheless, that's about what I should see. And again, if you're intermittent duty, assuming you're not blasting the thing with a whole bunch of high peak torques, then you're going to get more than 3 to 4 years. But the differential between the two means that one's going to fail before the other one, and therefore you have to account for that ease of replaceability. On small stuff, you know, when you're talking less than, say, 1,000 watts, I don't think it's a big deal. Just replace the gear motor. But on the bigger stuff, this gets really pricey. And, you know, we've done gearboxes up to 25 kilowatts on tube benders and whatnot, and those things will set you back. So with this, the Stober product line, you have the ability to buy their inline and right angle boxes for third-party motors, and you have the ability to buy an integrated motor. And there's an interesting thing about Stober that I will mention, because Stober has a relationship with Allen Bradley, who has a high market share in this country of servo-based applications, especially in the food and bev industry. Now, food and bev industry servo applications aren't the most challenging, but they're certainly numerous, and there's a lot of market share there. Stober makes a motor that, in essence, matches right up to the Allen Bradley servo gearbox, servo controllers, the amplifiers. And in fact, Allen Bradley uses the Stober motor in their product line. So it's a very interesting commercial advantage for Stober, in that if you're selling a Stober gear motor, its file is right in the, I forget what the name of the Allen Bradley amplifier is, their model name. It's the old Electrocraft design, I think. But whatever that servo amplifier is from Allen Bradley, you'll find this in the library, so it's an easy click and drag to set this Stober motor up on the Allen Bradley motion system. Okay, so with regards to Stober's product line, while they don't do a lot of worms, they do a lot of planetaries and a lot of right angle spiral and helical bevel gearboxes for precision applications. Now, I don't think this is kind of an exaggeration, but you're going to save a lot of length when you go to an integrated gear motor. You can see how compact that is. In this particular case, the Stober motor has the sun mounted on the motor shaft. Differential coupling, and obviously a much closer mount in terms of axial distance. Now, there's something else I want to point out about this, because we haven't talked about brakes yet. And in precision applications, most of the servo gear motors with brakes, the brake is a holding torque brake, which means you're not really allowed to use it for dynamic stops. Obviously, a dynamic stop, you have a whole lot more energy because you're dissipating the reflected inertia of the load in the gearbox and the motor in terms of the energy you're dissipating when you clamp the brake on. A holding brake is applied only at zero motion, and it does what its name says. It holds things in place. Most holding brake based servo gear motors will allow you 1 to 2 e-stops. After that, it's kind of like your bicycle helmet. They tell me if you fall down and you crack your bicycle helmet on the ground, you're supposed to replace it. So holding brakes for e-stop, once and done. This company makes a product that I want to point out to you because I'm quite impressed with it. And it's called Sure Stop. Oh, sorry, got to flip back to this presentation. Integrated dynamic brake, the key word being dynamic. This is an easy fit in between the servo motor and the gearbox. It means you can use their gearbox with their, I call it Sure Stop. I don't know if that's actually what they call it. Servo Stop, they call it Servo Stop. And then anybody's third-party motor. Not anybody's, but most third-party motors, I should say. So what you have here is a brake that will take dynamic stops, and that's huge for certain applications. There was an application at Disney that we ran into where they didn't realize that they had programmed the motion system to dynamically stop the servos under certain conditions and were shattering the static holding brakes. And they had to go and change them out. And it cost them a fortune. The ride was already in operation, believe it or not. So this, I think, is a significant product advantage for Stober's product line. Now, in the last 15 minutes, I'm going to go back to talk about harmonic and cycloidal gearing because it's really cool stuff. Now, find my doggone presentation again. There we are. All right, so harmonic gearing is basically a planetary geometry using a very innovative concept. I apologize for being so out of it this morning because I thought I had my ducks arranged, but this is an older presentation. I didn't put the harmonic on this. My fault. Okay. We depend on Google. Harmonic gearing is also called strain wave gearing. And basically, what's involved here are three parts. You have this part, which is on the servo motor shaft. And by the way, this is not a round, it's an ellipse. And then you have this part, which is an externally toothed flexible element. This happens to be a cup style. There are different styles of elements used, but the primary thing here is you have an externally toothed element that's flexible. You fit this ellipse inside it, and it distorts this elastically. It means it doesn't fail it, but it distorts it. And when you insert this inside the internally toothed ring of the final portion of the three key parts of a harmonic gearbox, this has two more teeth on the ID than this has on the OD. And what happens is you actually distort this thing and it walks around the internal toothed final piece, and that's how you get your motion. So the best way to illustrate this is to give you a video on it. Now, this is the major manufacturer of harmonic gearing, Japanese company.
Precision zero backlash harmonic drive gear component sets are key to the performance of our gearheads and servo actuators. Harmonic drive component sets consist of only three precision components: wave generator, flex spline, and circular spline. The wave generator is the driven or input element of the transmission. A hub having an elliptical shape is fitted within a special thin raced ball bearing to create the wave generator. The flex spline is a robust, torsionally stiff, yet radially compliant component with external gear teeth, capable of reliably transmitting high torque loads. The circular spline is a rigid ring with internal gear teeth. The circular spline has two more teeth than the flex spline. When inserting the wave generator into the flex spline conforms to the elliptical shape of the wave generator. Rotating the wave generator creates an advancing waveform on the flex spline. When assembled with the circular spline, tooth engagement occurs at each end of the major axis of the ellipse, and up to 30% of the total number of gear teeth are simultaneously engaged. The rotation of the wave generator causes the flex spline and circular spline tooth mesh to move around the circumference. Since the flex spline has two less teeth than the circular spline, rotation of the wave generator leads to a relative movement between the flex spline and the circular spline. Harmonic drive component sets, gearheads, and servo actuators are used wherever zero backlash, extreme precision, and high reliability motion control is required. Harmonic drive, advancing the technology of motion control through innovation.
Now that is some cool stuff. I am super impressed with the harmonic gearing design. Is it really expensive? Oh yeah, compared to planetary, but then not really when you need the features. Every robot that you can think of that's doing precision motion has harmonic gearing in everything from the shoulder to the elbow to the wrist Smaller robots may even have it in the base. The base is typically, on larger robots, too much torque for the harmonic gear, and therefore we go to a different style of zero backlash gear on that we will talk about in the final few minutes of our class today. But harmonic gearing is a fantastic product. Who thought of this? And today, as I said earlier, the market share is dominated by harmonic drive. Therefore, we all call it a harmonic gear. It's a Kleenex thing. The only U.S. manufacturer of harmonic gearing is Cone Drive. Cone Drive manufactures their harmonic gearing in Michigan, at the top of Michigan in Traverse City, in their factory there. There are probably a dozen Chinese people making this gearbox, some better than others. I think the Nidec product is reasonable in terms of quality. You can imagine that the quality here of this type of gearbox is significant in terms of its performance. Because if we go back to just this picture here, okay, it's not that hard to make this thing, right? The metallurgy behind this, because it's flexing all the time so that you can operate for longer life without the thing splitting. I mean, you ever take a paper clip and you go back and forth like this all the time? Eventually the paper clip's going to break. This metallurgy here associated with this flexible element is a monster technically. I know for a fact that Cone, in the initial designs when they were prototyping this decade and a half ago, were not getting the life that they needed out of these flexible elements. And they found out that they had micro grinding lines on these teeth. They had to go out and buy a $3.2 million grinder to solve that problem. This is a soup. Oh, Danny, do you have a question?
Yeah, what am I missing about the reduction of this harmonic drive? It's two teeth difference, right? There's got to be an output section that creates the reduction.
Well, okay, you can mount your output shaft right here, in which case, if you remember the video, this is turning at servo motor speeds, and this is counter rotating at the reduction ratio of the gearbox itself, depending on the number of teeth that you have on this. So you can mount your output shaft here, or you can hold this stable and mount a carriage on this and rotate the output ring. There's two different ways of going about it. These are components, and when you build up your gearbox, depending on whether you're going to use this as the output element or this as the output element, is going to determine the design of the gearbox. But the reduction ratio...
And the difference in diameter versus the difference in teeth count.
Well, I think it's primarily teeth count.
Yeah, this is Joe. Yeah, can you guys hear me?
Yes.
Yeah. So I think what he's asking is the gear ratio would be off, right, between the two pieces, and the answer in my understanding from engineering is that it's because the diameters are different. You're allowed to take two teeth out. Okay, they basically did the math that says two teeth is equal to the delta in the diameters of the inner and the outer teeth. Okay. And so the ratio coming out of the thing is equal to zero, the offset basically. And what's happening, I believe, is it's slipping. The gear is slipping, or actually spinning and not catching. Every once in a while, it catches the next tooth, right? Twice on a revolution.
Okay, I'll take a slight disagreement with you there. Remember, this is an ellipse, okay? Right. So it has a major axis where its diameter is greater than anywhere else on the ellipse. So let's just say this is the major axis. When I insert it into this flexible element, I'm distorting this flexible element such that along the major axis of the ellipse, it has the same diameter as the ID of the third element. And therefore the tooth contact occurs along the major axis of the ellipse. So when I spin this and therefore spin the major axis of the ellipse, the tooth contact between this ID and this OD gear set changes. And because there's two less teeth on this versus this, I get relative motion.
Yeah, okay. Perfect. Yeah, it's yeah, exactly. It's an ellipse equation then. That's right. Thanks.
And so, again, depending on the number of teeth on the on this interface between the OD and the ID, you get different ratios. Typically on the harmonic gear sets that I've seen, you're talking about 100, well, 70 to 150 is very common on a single reduction harmonic gearbox. Did that answer your question, Dan?
I think so, but I'm going to still Google it and look for some more information.
Okay, very good. So this is an extremely important technology in our gearing industry because it's got a superb set of performance characteristics, and at present is much more expensive, but it has compactness going for it. It has high reduction ratio per stage going for it. It has zero backlash going for it. One thing I'll say is that this is not a very stiff gearbox. Obviously not, because it's a flexible element. Reliability-wise, it's pretty reliable. Again, you've got special greases that have to be used. This is an extremely expensive thing to manufacture from a CapEx standpoint. The investment, it's a high barrier of entry to get into this market. And this bearing here is super critical. We've had a lot of issues in the initial prototyping at Cone on this bearing. We finally, well, we're owned by Timken now, so we got a lot of bearing horsepower behind us at Cone, and as such, we have good sourcing for this bearing. By the way, sourcing is another issue with this. If your bearings are so specialized, your metallurgy is so specialized, that you really have to have your sourcing issues solved if you're going to have any kind of decent deliveries. Now, if you are familiar with Harmonic, their deliveries, depending on the season, can go from 14 to 40 weeks. At Cone, they are relatively consistent at the 14 to 20 week range, but this is never, it's rarely a stocked item, if you will. Now, my point is, it's an important technology because as we get our act together and reduce the costs associated with this, it's going to push down on the lower technologies and eliminate them as the cost comes down to more of the level of the planetary inline, if you will. Any more questions on harmonic before I move to epicycloidal, Gary?
Hey, Pierce,
Yes.
just to clarify, I was looking at the difference of two teeth as the ratio between these two devices. It's actually the difference between the number of teeth in contact at any given time. That ellipse creates contact at two opposite points. So it's the ratio is the difference between the number of teeth in contact and the number of teeth in that output ring.
Okay, and I agree with that. Yes.
Yeah.
And typically, the difference in the total number of teeth on this element versus the output ring, if indeed this is the output ring, is 2.
Right.
And that causes the relative motion and therefore the reduction ratio. But again, bear in mind, this can be the output also if you hold this fixed, for example, in the housing of the gearbox, or this held fixed will cause this to rotate. And there's two different, it's just two different designs of the total gearbox. We're here again looking at the basic 3 elements of the gearbox, not the total. And then, of course, you have all the interfacing to mount your servo to this. So let's move to epicycloidal gearing, because that is the final, and stay with me because you don't want to miss this. The major manufacturer of epicycloidal gearing in the marketplace is Nabtesco. Now, remember I talked about involute teeth, and these are involute teeth, and notice that the contact area, the torque transmission, is right here where these teeth contact each other. When you go to this, you've got lobes. Much more contact area. And therefore an ability to transmit more torque in a more compact environment. Also, you got backlash in this type of gearing. If you reverse, you got a gap here, right? So it's going to, this one, if it's the driving gear, is going to jump the gap when you reverse. This is a true zero backlash situation. One of the other advantages of this versus harmonic gearing is this is super stiff. Look at all the contact that you have. There's no flexing elements here. You've got lobes on bearings here. So it's extremely stiff. This is an ideal gearbox for that antenna application I talked about earlier. But it is a planetary style gearbox with different shaped teeth. Sorry, an inline gearbox with different shaped teeth. It's not a planetary. So let's go and find a video on that, and that'll conclude our soiree this morning. I typically like to find Nabtesco's if I can find it. Where is it? Normally it pops up. Right, well, let's do this. There we go.
Hey everybody, Jeremy Morgan here, Innovative IDM, Business Development Engineer, Southeast Houston area. Today we're going to talk gearboxes from the largest manufacturer of cycloidal gearboxes in the world, Nabtesco. We're going to talk about their RV models today. So if you deal with robotics or machine tools, antenna systems, turntables, positioners, medical equipment, what have you, or even servos in general, this video is for you. Check it out. So this is the RV series gearbox from Nabtesco. And as you can see, this is just a plastic cutout version. Of course, all of them are metal. This is just so you can understand the inner workings of this gearbox. Let me actually show you this in action. You see here, this gearbox, it has 360 degrees of contact. And it's a two-stage reduction gearbox structure. And so what that gives you, it actually gives you a wide range of ratios to use within the same outer diameter, which makes it a more compact machine. And the high speed ratio enables you to use a smaller servo motor, which will reduce your servo motor cost. And it gives you enhanced machine accuracy plus reduced heat buildup. So the pin and gear structure here you see is built to give you a minimal backlash of less than 1 arc minute. And you also get high shock load resistance. So these gearboxes can actually withstand 5 times the rated torque, which is really impressive. And so the integrated outer load support bearing structure you see here, that's built in to help absorb external forces and torques, which allows a large load capacity as well with no additional support structures. So that's also, the pin and gear structure is going to enable you to have enhanced machine accuracy and durability. So the two-sided structure here gives you a high torsional rigidity, minimal vibration, high torque, and a minimum installation space requirement. So these guys are pretty easy to maintain. All you have to do is just grease or oil the gears from time to time. It all depends on how rigorous you're using them in an application. And because of these gearboxes and the ratios that it has, and being able to potentially use a smaller servo motor, is also going to give you energy savings as well in the long run. And what's really, really cool about these gearboxes is that you get a very low breakaway torque as well.
Now, Tesco always uses this planetary primary to get the ratios that they want for the main gear set, the epicycloidal gear set. Cone also makes an epicycloidal gearbox, and their brand name is Spinea, and that's it's a company that Timken bought out of Slovakia, the last half of the former country's Czechoslovakia. Spinea has been the traditional gearbox manufacturer for KUKA and ABB robots, so they have a very good pedigree in the industry as well. Now that they've got the billions of dollars of support of Timken behind them, and the fact that it's marketed through Cone Drive, it's a division of Cone Drive now. What I wanted to point out is that we don't necessarily need this to obtain the gear ratios. We will direct drive this disc with the servos in the cone design. So that's an advantage over Tesco's design.
So let's get down into the specifics as far as how cycloidal gearboxes work for those who would like to know. So here's the layout of a cycloidal gearbox, and let me actually go over the principle of operation as far as how these cycloidal gearboxes work. So the rotation of the servo motor is transmitted through the input gear to the spur gears, and then the speed is reduced according to the gear ratio between the input gear and the spur gears. The crankshafts rotate at the same speed as they are directly connected to the spur gears, right? Two RV gears are then mounted on the crankshafts with needle bearings, as you can see here. Then when the crankshafts rotate, the RV gears rotate eccentrically. So what happens after that is the pins are then arrayed in grooves inside the case. The number of pins is always one more than the number of teeth on the RV gear. Okay, so when the crankshafts make one complete rotation, the RV gear teeth then rotate one step in opposite direction. So the rotation is then transmitted to the output shaft via the crankshafts. The rotation speed of the crankshaft is then reduced according to the number of pins. So ultimately, the total speed is a product of the speed ratio of the first and second stage reduction. Pretty cool, right? Okay. So let me touch on lubrication as well. I kind of touched on it before.
And again, you can drive. You don't need this primary gear set. You can drive the final stage directly, which is again something that Cone offers in their Spinea product line.
But I wanted to talk a little bit more about it. So lubrication is pretty essential to the proper functioning of a gearbox. As you see here, Tesco actually has their own proprietary grease.
I'm going to stop it here because we're running way over time. By the way, harmonic and epicycloidal lubrications, you definitely want to buy them from the manufacturer. Cone offers their own as well. That's a big part of the engineering associated with the life on these boxes. So it just makes sense to make that the responsibility of the manufacturer. So we've covered a pretty wide range of boxes today. It's 8:10, and thank you for allowing me to go over time. Next week we will have a I'll show you the schedule coming up. So we are here on next week. We have a network remote I/O connectivity and junction blocks. That's Chris O, my colleague at Western Automation. We then have 2 more weeks of VFD class, the problems caused by current technology VFDs and the seminal innovation of matrix VFD technology that Yaskawa has introduced to the marketplace. I will publish the rest of this schedule, and you'll see what we have out through March 6th, and then I've got a couple of gaps to fill beyond that. Thank you very much. Time to go to work, and we will see you next week.